changes when the table rotates. There are two important transformations, which we'll get to a little bit later, but to transfer from joint space to tool space, we use the forward kinematic transformation, and to transfer from tool space to joint space, we use the inverse kinematic transformation. So one note here is that industrial CNC machines will actually perform the position control of each axis in joint space, although the tool paths are interpreted in tool space. So the machine has to interpret what does the programmer mean by tool space in order to control the joints to that position. A 5-axis machine will usually have what's called tool center point control, which is a code that we can enable in the program that rotates the workpiece coordinate system with the rotary axis. All right, so how is all of this actually done in a machine tool controller? So as we said, CNC computer numerical control is a digital control system that is pretty good at reading G-code and executing most G-code tool paths. One of the things that we see, however, in almost every CNC on the market today, and when I say CNC, I'm referring to the controller itself, is that the architecture is very proprietary, so we can't easily modify it. The manufacturer of the control doesn't provide us with ways to do things that we might want to that the manufacturer would rather us pay for. So if we want to do something special, we would have to call the manufacturer and say, I have $100,000, can you make the machine do this?
I think $100,000 is a bargain. I don't think they would do it for $100K.
Maybe a couple $100,000. So different controllers have different levels of what's called openness. Some are easier to modify. Some controls actually provide some limited amount of modifiability. Some provide none. That depends on who makes the control. But regardless of how open it is, all the control systems consist of a couple basic building blocks. We have an HMI, or human machine interface, which is usually a PC-based touchscreen. And then we have a real-time motion I/O control system. This consists of an interpreter, a trajectory planer, and interpolators. And then we have the servo drives themselves, which actually are what perform the closed-loop position control of the axis servo motors. So here is a high-level overview of what this looks like and how all the pieces fit together. We have two subsystems within the CNC system. We have non-real-time, RT stands for real-time, and we have real-time. Real-time means that this system executes a sequence of operations at some predefined period with a known maximum bound on the amount of what's called jitter, which is error that we can have when the next sequence of operations will be executed. So we would use a real-time system for safety critical control applications where, for example, we absolutely need to check the status of something every 1 millisecond, and we cannot tolerate any more than 100 nanoseconds of jitter. This is in contrast to a non-real-time system, which would be a typical Windows PC, where things can take as long as Windows decides they're going to take to do something. So for safety critical things, we use real-time. For non-safety critical things, we use non-real-time. So in the non-real-time subsystem of the CNC, we have the HMI, human machine interface, which the operator interacts with. We then have a program interpreter. The program interpreter is responsible for reading the G-codes from the program or command line input and translating that into a format that the real-time system can understand. So it will route motion primitives or program support commands, M codes, to the appropriate place. So we'll talk about the motion primitives. So as these traverse from the non-real-time to real-time system, first they enter the trajectory planner, which runs in a real-time thread with a thread period of T sub TP. The trajectory planner is responsible for determining the velocity profiles or positional derivative profiles or some parameters about the positional derivatives of the motion that is to be executed. Typically this will be the speed. This information is then passed to the interpolators, which run with a thread period of T sub interpolator. The interpolators then command the 5-axis servo loops, which run at an even faster thread period of T sub servo. So we'll talk about each of these in a moment. But outside the CNC system, we have an offline CAM system and post processor, which creates G-code that enters the program interpreter. We also have a data collection PC that collects data from the machine in some format. Here it says MT Connect. There are a number of different options. We will talk about those in a moment. So one of the most important aspects of the motion control system is the trajectory planner. And as I said, this is responsible for assigning positional derivative profiles to the motion to be executed by the machine. So first, the interpreter will read the G-codes, decompose these into primitives, route the motion and auxiliary commands to the appropriate subsystems, decompose CAN cycles, and then eventually we'll end up with a list of motion primitives. The trajectory planner runs in the real-time subsystem, and this reads primitives off the motion primitive list, and then creates rough position and velocity commands at the T sub TP thread rate to be sent along. Usually, this will be some kind of proprietary trajectory planning strategy, but for an example here, I've shown what a particularly common implementation is, which is called a trapezoidal velocity profile. So the reason why it's called trapezoidal velocity profile is because the velocity takes on the shape of a trapezoid. So here's the beginning of the move at time 0. The machine will command the axis to accelerate at some constant rate up until the cruise velocity here. It will then cruise along at that velocity for some time, and then it will decelerate at a constant rate back down to the end of the move. So this results in step changes in acceleration and impulses in jerk, which is the derivative of acceleration. And finally, the position profile looks something like this, where we have a quadratic segment at the beginning, linear, and then another quadratic segment at the end. This is not the only way to plan trajectories. This just happens to be a common way. And this actually is a special case in which there are not consecutive moves. If we have 2 moves in a row, then we use what's called look ahead, which is where the machine reads ahead of its current position to determine what the next move is and how fast it is allowed to travel in order to not overshoot at the end of that move. So this increases the performance for toolpaths with consecutive moves, obviously. So it's kind of akin to when you're driving down the road and there's fog in front of you. You slow down because you can't see as far in front of you, and it takes you some finite amount of time to stop. So the last thing we want to do in a CNC application is overshoot the commanded endpoint. So that is what the look-ahead buffer is for. So in this example, we have 2 segments of look-ahead. We are currently at this position here, all traveling along block NI. The next block is block NI plus 1, and for the sake of this, let's assume that both blocks are of length L. So here's the look-ahead depth. So we can see until the end of this block, and the machine actually has to assume the worst-case scenario that this block is the end of the program, because otherwise it may overshoot. The trajectory planner look-ahead only has a finite size. So it will determine how fast it's able to go by considering the maximum rate of deceleration of the machine, and then it constructs this curve here that shows the maximum velocity it can travel along the move in order to reach this point without overshooting. So the size of the buffer is usually dictated by the machine parameter, that is the number of blocks that are within it. And as you can see from this discussion here, actually the smaller these blocks get, the slower we can go, the slower the machine is going to go along the path to avoid overshooting the end of the buffer. So last note here is about data feedback. I mentioned MT Connect as a way of feeding back data from the machine. And so MT Connect is an open standard that is a read-only way to get process data from the CNC. And this is something that you can actually download online and implement yourself, but typically a lot of newer machine tool builders will have implemented their own form of MT Connect, and we can read data at usually a low rate, which is about hundreds of hertz or so at the very most for a commercial off-the-shelf implementation of Kuma. And but the data rate is not actually defined by the standard. It's limited by the implementation of the standard. It's just that most machine tool builders have not implemented anything much faster than that. Another option is what's called OPC-UA, or OPC Unified Architecture. Some machine tool builders use this to accomplish a similar goal of providing process data feedback from the machine. OPC-UA, instead of being read-only, is actually read and write, but the idea is similar. We also have some proprietary application programming interfaces where we can interact with the machine. Maybe we can read I/O points or something like this. These will be provided by the machine manufacturer, but these will run also in the non-real-time system. And this will typically be low frequency as well. So a good example is the Akuma Think API, or Mazak also provides an API for their smooth control. So that covers all the building blocks, and so let's talk about
the hundreds of hertz means about 50 times a second. Just go back to the previous slide. I want to make sure I understand. Less than hundreds of hertz. What do you mean by that? 50 times a second?
Less than a few hundred hertz is the highest. It's a non-real-time thing, so they can claim we can do 500 hertz. Actually, they claim 1,000 hertz, but we see about 300 hertz. So some hundreds of hertz and less, and lower. So hundreds of hertz is the fastest.
So more than 100 hertz?
No.
You said 300.
Okay.
I'm just confused by the phrasing.
So the fastest.
So it's 300 hertz?
Fastest commercial implementation is approximately 300 hertz. Yes, and all of them will be
so
below.
That means 300 times a second.
Correct.
Okay. Thank you. So that's pretty fast, or is that not fast enough?
It depends on how fast you're driving the machine, I suppose.
Well, I have a hard time understanding whether this is good or bad.
Okay.
Seems to be very good for robotics, isn't it?
Well, typically a servo loop will be on the order of kilohertz. The actual position control will be on the order of kilohertz, and in